Here's a more practical relative motion example where we have a plane traveling 300 kilometers per hour in the air. We have a wind moving from the west, and it's 40 kilometers per hour. We're going to look for the velocity of the plane relative to the ground in these four different situations. So the plane traveling east, west, north, and then at an angle of south 35 degrees west. So in example A, we have the plane traveling east, and we also have the wind moving from west to east. So that leaves us with a diagram that looks something like this. This first vector here is the speed of the plane. And we have a second vector, which is our wind speed, 40 kilometers per hour. So that gives us an equation that looks something like this. The plane's velocity relative to the ground is going to be equal to the plane's velocity relative to the wind plus the wind's velocity relative to the plane. That leaves us with 300 kilometers per hour, and we're going east based on our diagram. We're going to say that in this case, east is positive, plus 40 kilometers per hour east. And since they're all in the same direction, there's no trigonometry that has to go on here. So that leaves us with a simple addition, 340 kilometers per hour in the east direction. So this is just a one-dimensional motion question in essence. The next one is similar. Now we have the plane traveling west. So that means our plane is traveling in this direction. So now we've got 300 kilometers per hour, but moving right to left instead of left to right, like in the previous example. And then we have our wind speed of 40 kilometers per hour traveling left to right. So you want to decide what your directions are going to be here. So if we're going to stay consistent, we're going to say that moving to the east is positive, moving to the west is negative. So that leaves us with an equation that says the plane's velocity relative to the ground, the plane's velocity relative to the wind, plus the wind's velocity relative to the ground. So in this case, my plane is moving east to west, so I'm going to denote that as negative, right? So I'm going to say negative 300 kilometers per hour plus the velocity of the wind, which is positive because it's moving to the east, is 40 kilometers per hour. That leaves us with negative 260 kilometers per hour. And to report this as a positive value, recall that because I said that east is positive, that means west is negative. So this is a negative value. That means that my resultant vector is 260 kilometers per hour in the west direction. Part C is asking what happens when the plane is traveling north. So we're going to add north to our directional vectors here. So north and east are positive. We should start off by drawing a diagram because now we have two-dimensional motion, right? We're going in the north-south plane and we're going in the east-west plane, so that's two-dimensional. So our plane is traveling north, and that, of course, is 300 kilometers per hour. And the wind is traveling east or west to east, sorry. So that's 40 kilometers per hour. So this obviously, we're going to finish off this triangle and we're going to need to solve for that angle. So the hypotenuse of the triangle is the plane's velocity relative to the ground. And we can solve this by using our Pythagorean theorem. So the plane's velocity relative to the ground is equal to one side, so 300 squared, plus the other side, 40 squared. That's going to give us 302.7 kilometers per hour. And we need to solve for our angle. So theta is equal to tan minus 1 of 40 over 300. And that gives us an angle of 76 degrees. Now that's north 7.6 degrees. So north 7.6 degrees east. So we would say that the plane's velocity relative to the ground, 302.7 kilometers per hour, north 7.6 degrees east. Finally, we're looking at the plane's velocity relative to the ground. If it travels at this weird angle, south 35 degrees west. So here it's really important that we draw an accurate diagram. So it always helps to draw just a tiny Cartesian plane where you're going to start your diagram here. So south 35 degrees west means we're starting down here at the south end. We're going to estimate about 35 degrees. So it's going to look something like this. So here's our first vector, 300 kilometers per hour, and that's approximately south 35 degrees west. And then, of course, our wind speed is going to be something like this. So that's 40 kilometers per hour. We can finish off this triangle. And it's really important just to remember that this angle down here at the bottom right, this is not necessarily a right angle. So depending on how you draw your picture, it might look like a right angle, but just don't assume that, because that's going to lead you to making assumptions, which are going to eventually lead you to making a mistake. So this here is our plane's velocity relative to the ground. In this case, we're going to use our cosine law rearranged to solve for the side we're looking for. So that leads us with our plane's velocity relative to the ground equal to square root of side A plus side B minus 2 times side A times side B times the cosine of the angle opposite to the angle you're solving for. So that means we're solving for this angle, or that means we're looking right now at that angle right in there. To determine what that angle is, we're going to use a Z pattern. So there's a Z pattern here. I'm going to highlight in green. So there's a Z pattern right here, which means that this angle is the same as this one. Well, we know that if this angle inside the one that we decided here, if this angle from here to here is 35, well then this green angle here has to be 55, which tells us that this angle here has to also be 55. So that gives us cos of 55. We can solve this expression, and that leads us to 279 kilometers per hour. Because this is not a right triangle, to solve for the angle that we need for this question, we need to use our sine law instead of our SOHCAHTOA trigonometry. So what we're solving for is this tiny angle inside here. This is the angle we're looking at. I'm going to call that angle alpha. So that tells us that sine of angle alpha over the opposite side, which is 40, is equal to sine of another angle, another one that we have is 55, divided by the length of the opposite side, 279. Rearrange this and solve for alpha, and that leads us to 6.74 degrees. Now, that's just the angle within the triangle, so I need to get a better angle relative to one of my four directions, right? North, south, east, or west. Well, if that's the case, then I know that the entire angle that I'm dealing with right here from west down here, again, it's not a right angle. I know it looks very close. It's going to be 55 plus whatever we just solved for. So the angle that we actually want, theta, 55 degrees plus 6.74 degrees. That's going to leave us with an angle theta of 61.74. We're going to just round that up to 62 in our final answer. So we'll say, therefore, the plane's velocity relative to the ground is 297 kilometers per hour west, 62 degrees south.